students, in physics, now let us see another experiment. This is also from the section mechanics. What this says is determination of the relative density of a liquid using a U tube. In the laboratory, you can find a glass tube in the shape of U, letter U, right. It will look like this. That is how it will look like. Right. And usually it will be fixed on a wooden scale, wooden board like this. And sometimes the wooden board would have scales on both sides. If not, you have to fix a scale, right? You will have to fix a scale. On this side, you need a scale. Similarly, on the other side also, you will have to fix a scale. This will be scale. Similarly, scale on the other side also. Right. So, now what we are going to do, let us say you want to find the relative density of oil. So, the two liquids that we are going to use here are water and oil. So, what we will do, we will fill water into this first, right. Let us say you fill water. So, once you fill water, it will fill both sides to the same height. That is how it will be, right. After filling that with water to a certain level, now to one of these limbs, one of these arms, you fill some oil. Oil is the liquid to which you want to find the relative density, right. So, to one of these arms, not for both of them. Let us say I am going to pour it on this side. So, once you fill oil, oil can't just stay on top of this, because when the oil comes here, then the water will be pressed downwards, it will go up a little bit. So, how it will look like after I have filled oil also, look at this. Water will be like this. See, this will be the column of water. On top of that, you will have oil. This is how the equilibrium will come. Why is the oil column taller than the water column? Because of the densities. I am going to explain that. So, this is how it will look like. Water will be here. On top of that, in one of the arms, you will have oil. Now, let us calculate the pressures. Pressure at each point. See, I will show you the points. At this horizontal level, same horizontal level, think about this point and this point. Let me name that point as A, let me name this point as B. Let us write pressure at A. Pressure at A is going to be, I need this height, let it be H O, let it be H O. This side, the height of this oil column, let us call it HO. Similarly, the height of the water column, let us call it HW. So, pressure at point A is going to be, see, this is the atmospheric pressure, let us say phi atmospheric pressure, plus H oil, rho oil G. We studied that if there is a liquid to the height of h, the pressure given by that at the bottom of it will be h rho g. So, it is oil, h oil, rho oil, g. And what about Pb, pressure at point B? Again here it is atmospheric pressure plus HW rho W G, HW rho W G. But A and B are at the same horizontal level within the same liquid. Can you see? It's connected liquid, is water at the same horizontal level. What can you say about the pressures? Pressures must be equal. So, PA and PB must be equal. PA equals PB. Pi plus H oil rho oil G, pi plus H water rho water G. Pi and pi will be cancelled. H oil rho oil G, H water rho water G. H oil will be equal to rho W over rho oil into HW. Or if I write the other way around, if I make HW the subject of it, HW will be equal to rho oil over rho water into HO. Throw this in the y-axis, x-axis, you will get y equals mx graph. How do we get y equals mx graph? You need to change HO. HO means the height of this oil. So, what you can do, you can start with a smaller length, say 10 centimeter, then put another 5 centimeter height of length, another 5 centimeter. Likewise, you can change this HO. When HO is changed, accordingly the equilibrium position will change. What will happen when HO increases? This point will come further down, right? So, the common interface will come further down, this will go up, so HW will increase. You can't do it other way around. If you put water into this, HO wouldn't change, equilibrium position will change, HO is going to remain the same because you have the same amount of oil, right? So, you can't do this experiment by adding water into it. You have to do this experiment by adding oil into this, then only you will get different HO and HW values. If you add more water into this column, what will happen? This point will go up, the interface, this is what you call oil water common interface, that will go up, and then HO and HW will still read the same values. So, once even they asked in the exam, why do we add water, why do we add oil into this rather than adding water when we want to get multiple readings? If we add water, oil column's height doesn't change, which means HO, HW, you will get the same readings again. Clear? That's one. Second thing, why do we add water first and then oil? What if I filled oil first? If I filled oil first, look at this. That's how your YouTube is. Say if oil is up to here, then when you pour water into it, what will happen is, the water might sometimes penetrate through the oil because water is highly dense, right? And you may have a situation like this afterwards. Water might have gone to the bottom, you may have oil on both sides. Why? When water goes to the bottom, it will stabilize in bottom. So, on this side column also, you will, on this limb also you will have a oil column. On the other side also there might be oil column, which can complicate the experiments, right. So, to avoid that, usually more dense liquid has to be put first and then only the less dense liquid has to be put. So, that is how we are going to do the experiment. We take the U-tube, fill it with water to a certain level, and then you fill with different amounts of oil every time you measure the HO and HW. HO, HW means above the common interface, how much height is there for oil and water, right. Materials and apparatus, you need a U-tube, 2 half-meter rulers for both sides, coconut oil because we are going to find the density of coconut oil only, water, clamp stands and a set square. Why do we need set square? You know, when we take the readings, understand this, this is how the meniscus will be, the water column or the oil column will have a meniscus shape like this and the readings are going to be here. So, what we do, we will keep a set square, like this to be See, one side of the set square will be kept like this, other side will be like this. So, we keep the set square like this and get the reading, so that we can get the exact reading, right. Understand, meniscus lower point is what we take as a reading, and that also we keep a set square and get the reading. When I do the experiment, I will show you that. So, that is what the set square is. Theory I already have explained to you, HW, HL, then you balance the pressure at the common interface. Now, this is what you call oil water common interface. So, at that horizontal level you balance the pressures. We get the same formula, HW equals rho L over rho W. I use rho oil, they call it rho L over rho W to HL. Rho L over rho W is what you call relative density of liquid. So, if you get the gradient of the graph will give you the relative density. Look at the method. Attach the U-tube vertically on the stand. Fix close to this the vertical limbs, the half meter rulers onto the stand. Pour a certain quantity of water into the limb of the U-tube and then pour it into the other limb another quantity of coconut oil. So, first you put the water and then the coconut oil. Using the set square, obtain respective readings x and y for water meniscus and liquid meniscus, and then the reading corresponding to the oil water interface correctly. Common interface also you have to take it. Adding more of coconut oil in small quantities into its limb, obtain about 6 sets of readings, 6 or 5 sets of readings for x, y and z. X, y and z means x, y, one is the meniscus of water, one is the meniscus of oil, and that will be the interface. So, x minus z is going to be one column's length, y minus z is going to be another column's length. So, every time you have to get 3 readings, because common interface also will change. When you put more and more oil, it will come further and further down. Since it comes down only, other side water column increases, right. So, that is what the experiment is. Let us do this very simple experiment. Let us get the readings and see what relative density we get for oil. You can see the apparatus here. This is the primary one. This is what we call U-tube. Can you see, we have a U-shaped tube. Can you see? It's a U-shaped tube. And there is a scale here. Both sides of the tube, we have a scale here. Suppose the U-tube you have in your laboratory, if it does not have scale fixed on it, you can take 2 half-meter scales, half-meter rulers, and fix it along with it, right. Besides the tube, you can fix the meter ruler, right. So, this is what we call U-tube. When I do the experiment, I will show you how we are going to use it and how the concept is being applied, I will show you. This is a beaker with coconut oil. The relative density of this coconut oil we are going to find, and this is water, right. That is all the materials and apparatus we need for this experiment. Now, let us see how we are going to arrange this and what procedure we are going to follow to find the relative density of this coconut oil. Students, you can see I have fixed the U-tube on a vertical plane. That is essential. When you are fixing it, make sure it is on a vertical plane. And see, what we are going to do here, we will fill this with water, right, to a certain level, maybe up to 15-20 centimeter, depending on the length of U-tube you have. I have one up to 45 centimeters. So, approximately to half of it or less than, a little less than half of it, I will fill this with water. So, the water will remain in the bottom part of this U-tube. Then what I will do, on one arm of this U-tube, on one side of this U-tube, I will fill the coconut oil in it. So, what will happen in that arm or in that side tube, coconut oil will fill for a particular height. Let us say it fills for 10 centimeter. So, because of the pressure that coconut oil exerts, on the other side water level will have to go up. So, what we will do, water oil interface, at that point if you check the pressure, that pressure has to be equal to, above that interface what do we have? We have the column of oil, and on top of that it is atmosphere. So, at the water oil interface, pressure is going to be equal to atmospheric pressure plus the pressure exerted by the column of oil, which will be H rho G. If I say H O for oil's height, rho O for oil's density and G for gravitational acceleration. So, A atmospheric pressure, A plus H O rho O G will be the pressure at the interface, which interface? Water oil interface. At the same height, if you move on to the other side, you know, below what we have is water. Pressure has to be same. Above that point, what you have on the other arm of the U-tube, it's just the water only. If I find the height of that water, let it be HW, then the pressure at the same height point, same point as of water oil interface, on the other arm at the same height, pressure that we can say A atmospheric pressure plus H rho G of water, HW rho WG. Since both points are connected by water, continuous water, we can say both pressures have to be equal because they are at the same height, which means A plus HO rho O G, A plus HW rho WG will be equal. Both sides you can deduct A will be out, then you will have HO rho O G and HW rho WG. G can be nullified, then what remains? HO rho O and HW rho W, both will be equal. So, if I can measure the oil's height and if I can measure the comparable water's height, HO, HW will be known, then I can say HO over HW or other way around, HW over HO will be equal to rho O over rho W. Rho O over rho W is what we call relative density of oil. So, actually one reading is sufficient for me to find this relative density, but still in physics most of the experiments we go for the graphical method to improve the accuracy. So, here also that is what we are going to do. We will take multiple readings of HO and HW, draw the graph HO versus HW, HO on the x-axis because oil's height is what we are going to change. Maybe we will start with around 5 centimeter height of oil, then add some more oil, make it around 10 centimeter, 15, 20 centimeter approximately. You increase the oil's height and at each instance find the height of water column. So, HO versus HW, HO on the x-axis, HW on the y-axis, you draw the graph, the gradient of the graph will give you relative density of oil that we have used here. So, that is a very simple experiment we are going to do. Observe carefully how we do this, how we get the readings. 4 or 5 readings would be sufficient for us to draw the graph, right. So, as I mentioned, first I am going to fill this U-tube to a certain height with water. Since the diameter of this tube is very small, rather than filling it directly, there might be spillages. So, I am going to use a syringe here to fill this without spoiling the scale, right. You can see the bottom of the U-tube, the water is filling it there. We need more water because on one side when you fill it with oil, oil will pressure the water. So, water will move to the other side. We have to make sure oil is always only on one arm of it, otherwise the calculations will not be done, cannot be done. So, let us fill more water. It has almost come to 12 centimeters, almost at 12 centimeter. Let us fill more. After filling it with water to the desired level, give it some time until the levels become balanced, and sometimes the internal wall of this tube, there might be some water drops stuck on it. So let it fall down and it comes to a stabilized level. After that, what we should do, only to the one side of either side of it, either on that side or this side, to one arm of this U tube, I am going to fill with oil. Now it has come to some equilibrium. You can see both levels are equal. It's approximately 18.5 centimeter. Approximately it's at 18.5 centimeter, right? We don't need this reading right now. That is enough for us. That level of water is enough. What should I do next? Take some oil and fill it on one side of this U tube. Let me fill it to this side. Initially, I will start with approximately 5 centimeter, 5, 6, 7 centimeter, and then I am going to increase it by approximately 5 centimeter every time. So let's put a little bit of oil there. Now you all can see, this is the column of oil, and then we have water continuously up to here. Since the background color is also yellow, you might not be able to see the oil column clearly. I will just keep a black color sheet behind and I will show you the oil column separately. You can see here, this is what we call water oil interface. Can you see? Up to here we have water, and this is the column of oil. That is a column of oil. From this point we have water up to here. So understand, at this point if I check the pressure, that pressure has to be atmospheric pressure at this point A plus H rho g of oil. At the same height on the other side, see at the same height here, at the same height on the other side, if you check the pressure, that will be A plus H rho g of the water. A plus H rho g of the water. See, at the same height. Since it is connected by water, the pressure at this point and pressure at the same height on the other column should also be equal. That is what I mentioned earlier. A plus H rho g of oil, A plus H rho g of water on the other side have to be equal. From that only we got HO rho O equals HW rho W. So the readings we are going to get, we will get the reading at this point, water oil interface reading we will get, and we will get the reading at this point. You have to be careful when you get the reading at this point, you will see a meniscus there. In the meniscus, you have to take the bottom of the meniscus reading, right? It's a curve, meniscus is a curve, right? So which reading we get? The meniscus, bottom point of the meniscus reading has to be taken, right? So the reading here, difference will give us the height of oil column. And then we will get the reading at this point, water level. That reading minus the interface reading will give us the height of water column. Right? That is all the readings we are going to get. So every time we have to take 3 readings, one of the interface, because when you put more oil, what will happen? The interface will go down and the water will come up on the other side. So all 3 readings we have to take again. 5 times we are going to take readings like this. That means we will have 5 sets of HO and HW readings. With those readings we can go for a graph. From the graph we can find the gradient. Gradient should give us the relative density of the oil we are using. Shall we get the readings now? The reading at this point, water oil interface is 15.8 centimeters. You have 15.8 centimeters. Reading at this point, the oil levels reading 24.3. Actually, when we do the experiment in the laboratory, we don't keep the apparatus like this. We have to keep the apparatus right in front of us. The reading has to be kept at your same eye level, and that's how you have to get the reading. Here, since I have to show you more clearly, I have arranged the apparatus like this. When you are doing the experiment in your laboratory, you have to keep the apparatus in front of you. The scale has to be right in front of you, and your eye level must be at the same level of the reading you are taking. Ensure you follow all those procedures when you are doing it yourself. Here, since I have to show you more clearly, I have kept it like this. Right. So the reading here we have is 24.3 centimeter. 15.8, 24.3, we have 8.5 centimeter as the height of oil column. On the other side, the reading here, that means the water level, the meniscus reading there is, the water level meniscus reading is 23.2 centimeter. 23.2 centimeters. So from 15.8 up to 23.2, we have 7.4 centimeters height water. So that is the height of water, HW. Right. So we have got one pair of HO and HW. Actually, with that itself we can calculate, because HO rho O equals HW rho W. If you substitute these values, you should be able to get rho O rho W, which is the relative density of oil. Still, since we want to go for a graph, we need multiple readings. Straight line graphs, we prefer at least 4 or 5 readings to get accurate answer. Right. So I'm not going to stop the experiment with this. I'm going to get another 4 readings. How do I get another 4 readings? I'll add more oil to this little by little, increase the height of oil column, and then get the readings. So let's add some more oil into this. Once you have filled it with some more oil, you have to give it some time, because oil on the internal walls of this tube might take a while for it to fall down and stabilize. So wait for a while until the levels get stabilized and remain same, and then only you must get the readings. Otherwise, there can be errors in the readings. I can show you again. Look at this. Can you see the interface? Water oil interface. This is the oil level. This is the level of water. Those are the 3 readings we have to get. Oil water interface reading, oil top level reading. On the other arm of the U-tube, the water top level reading. That's all we are going to get. The interface level is at 13.5 centimeter. Water oil interface is at 13.5 centimeter. And the oil level, you can see here, it is at 27.2. 13.5, 27.2 means that is 13.7 centimeters height. 13.5 here, 27.2 here. So if you get the difference, 13.7 centimeter is the height of oil. And the height of water, the reading here is 25.4 centimeter. 25.4. So 13.5 is the interface, 25.4 you can get, that is 11.9 centimeters is the height of water. So that is what HW and HO we get as the second set of readings. We are planning to get another 3 more readings, so that we will have 5 sets of readings, and the graph will give us precise answers. So let's fill it with some more water, approximately another 5 centimeter, approximately, because you can't get it precisely here, approximately another 5 centimeter of water, 5 centimeter of oil. Let it stabilize. As I mentioned earlier, it will take a while for the oil in the internal walls of this tube to come down and come to a stabilized water level. Otherwise, what will happen? Before it stabilizes, if you get the reading, while you get the reading itself, the readings might change. So after you get one reading, before you go to the next reading, the heights might change. Therefore, you have to give it time until it stabilizes. Make sure the reading doesn't change and then get the reading. Students, now we will get the readings. The interface is at 10.7. Water oil interface is at 10.7 centimeters. This is at 10.7. And the top level of oil is at 30.7, 30.7. So height of oil we have used this time is 20 centimeter, 10.7, 30.7, 20 centimeter. The water level is at 28.1 centimeter. So 28.1, the common interface is 10.7. The difference will give us the height of water. So that's the third pair of readings, height of oil and height of water we can get from that. To get another two more readings, we had to add a little more oil into the other column. Let's add some more oil into that. As I mentioned earlier, let it stabilize, let it stabilize. Let's get the readings now. Water oil interface is at 7.9 centimeter, 7.9. The oil level is at 34.4 centimeter, 34.4. So 34.4, 7.9 difference will give us the height of oil. And water level is at 30.9 centimeter. So 30.9 and the interface level difference will give us the height of water. We have got 4 readings. 4 readings are actually sufficient, but we will get another reading. 5 readings will improve the precision. More the readings you have, better precision you will get, right? So let's add some more oil and get another reading. This time the interface is here, you can see water oil interface, it is at 4.7 centimeter, 4.7 centimeter is here, and the oil level is at 38.4 centimeter, 38.4, 38.4, 4.7 difference will give us the height of oil, and the water level is at 33.9 centimeter. So 33.9, 4.7 will give us the height of water. Right. So now we have got 5 different readings here. With these 5 pairs of readings, we can draw the graph HW versus HO. HW has to be in the y-axis, HO has to be in the x-axis. You draw the graph, you will get rho O over rho W, which is what we call relative density as the gradient of the graph. Right. Couple of restrictions we have here. One, the density of both, that means when we use water, water's density and the other liquid's density must be somewhat close to each other. If one is, say, if we are using water and mercury, what will happen? If water is at 1000, we know mercury's density is 13,500. You will get 13.5 times difference. The relative density will be 13.5. Then what will happen? To raise the mercury by 1 centimeter, you will have to put 13.5 centimeter of water. Then the height of this U-tube will not be enough to get 5 different readings and draw a graph. So that is one of the main difficulties we have with this experiment. The relative density must be somewhat close to 1, say 0.7, 0.8, 0.9 or 1.2, 1.3, 1.4, somewhat comparable range it has to be. Right? Otherwise, you will not be able to do it because the density, the difference in columns will be vastly different. Then the height of column you need to do the experiment and get 5 readings will be difficult. Let me show that to you using another U-tube and with mercury. Now I have taken another U-tube. Here I am going to show you what happens when we use water and mercury for this experiment. As I explained, mercury's density is 13,546 kilogram per meter cube, where water's density is 1000. So the relative density of mercury is 13.546. Because of this, what will happen? To raise the mercury level by 1 centimeter, you have to put a lot of water. Say around 13-14 centimeter of water has to be added to raise the mercury level by 1 centimeter. I am going to show you that here. Let's see. First, let me fill this with mercury because higher density one has to be filled first, right? You can see here the mercury level is here, both sides. Now what I do, let me fill one side of this U-tube with water and see what happens to the mercury when I fill this with water. You can see I have filled that with considerable amount of water. Look at the height of water column starting from here. Starting from here, it goes all the way up to here. Let's get the approximate readings. This is around 4.5 centimeter, approximately 4.5 centimeter. This is around 21.5 centimeter. So 4.5 to 21.5, we have around 17 centimeter height of water. For that 17 centimeter height of water, let's see how much of the mercury column has gone up. This is at 4.5. So the level here is at 5.7 centimeter. 4.5 interface, 5.7 here means it's just 1.2 centimeter. So can you see, to raise the mercury by 1.2 centimeter, I have to fill water up to 17 centimeter of height, approximately, with the approximate readings here. So imagine if I have to get another reading where I get another 2 or 3 centimeters higher of mercury level, I have to have like another meter of this U-tube. So getting 5 different readings with considerable height increments of mercury will be very difficult with mercury and water. This had been even tested in the exam questions after the routine structure type question. The last part they asked, what would be the difficulty you face when you do this experiment with mercury and water? Or what would be the difficulty you have in using this experiment to find the relative density of mercury? Questions like that they ask. So this is what the problem is. Mercury, the relative density is so high. So to raise it by even 1 or 2 centimeters, the water column's increment has to be much bigger. The height of YouTube will not be sufficient to get 5 different readings and do this graph, draw the graph, right. So just to explain that only I have taken this part. So hope you understood that. This is all we have in this experiment using the YouTube and finding the relative density of another liquid. We have used it for coconut oil. Now, with the readings we have got, let's draw the graph and see what results we get, what relative density we get. Students, you can see the readings I have recorded on a table. X, Y, Z, X, Y, Z. Z is the interface. X is the oil column. Y is the water column height. So if you want to get HW, you have to subtract Y and Z. Y, Z difference. 23.2, 15.8, 7.4. 25.4, 13.5, 11.9. This will be 17.4. This will be 23. This is 4.7, 29.2. Those are the height of water columns above the interface. Now the oil column 24.3, 15.8. That's going to be 8.5. 27.2, 13.5, 13.7. 30.7, 20.7, 20. 34.4, 7.9, 26.5. 38.4, 4.7, 34.1. Those are the HW and HL readings we have. Let's draw the graph. You remember the formula. HW equals rho W over rho L. No, rho L over rho W into HL. HL is what we were changing. That's why we take it in the x-axis. Accordingly, HW was the value. So, straight away the gradient will give you the relative density. HL in centimeters. HW in centimeters. HL you need up to 34.1. 4, 8, 12, 16, 20, 24, 28, 32, 36. HW has to be up to 29.2. 4, 8, 12, 16, 20, 24, 28, 32. First point, 7.4, 8.5. X-axis 8.5, 7.4. 8.5, 8, 10, 9, 8.5, 7.4, 4, 6, 7.4. Like that. 4, 6, 7, 7.4. Next. Next. 13.7, 11.9. 13.7, 12, 14, 13.7, 11.9. 13.7, 11.9. 20, 17.4. 20, 17.4. 16, 18, 17.4. 17.4. 23, 26.5. 23, 22, 23, 17, 23, 26.5. So 26.5 has to be in the x-axis. 24, 26, 26.5 and 23. 20, 22, 23. Right. 34.1, 29.2. 34.1, 29.2, 28, 30, 29.2. Right. That's how you get the points. Let's draw the straight line. Seems like we'll get a nice straight line through origin. Let's see. Right. Only the last point has deviated a little bit. Apart from that, everything else goes through the point. Correct? Yes. Let's get 2 points to find the gradient. Gradient. Here this point is good, which is at 29, 30 and 26. 30 and 26. Then we can take another point where maybe this point, that's at 14. This was 30, yeah, 14 and 12. 14 and 12. So the gradient you're going to get 26 minus 12 is 14. 30 minus 14 is 16. 7 by 8. 7 by 8 means 0.8. Then 70 you have. 7 by 8. 60. 7, 5. 0.875. 0.875. So the relative density of the oil, rho L, rho liquid divided by rho W is 0.875. So if I take the density of water to be 1000, then the density of oil that we have used is 875 kilogram per meter cube. Clear? That's what the graph readings and how we do the calculation based on the graph. Right? So practice this again. Now let's see some past paper questions on this experiment. Let's see a past paper question from this experiment. See, I have taken 2003 paper. You are given the following to find the density of coconut oil. A U-tube with relevant scale and fixed on a vertical frame. Water and required amount of coconut oil funnels. You are given all that. Draw the labeled diagram of the experimental arrangement that shows levels of water and coconut oil columns and the common interface clearly. We know very well. That's what the experiment we have done now. Let's draw the limbs or arms of the U-tube. This is one limb. This is the other limb. Right. That's what our U-tube is. Let's mark the water level. Make sure you mark the meniscus, not the horizontal level. It must look like the meniscus. And on top of water, let's mark the oil column. Right. Let's name it. This is the level of oil column. oil column. Level of water column. And this point is the common interface. Common interface. Right? They ask you to mark all these three clearly. Next part. Mark the measurements that you have to obtain as H1 and H2 in the above diagram. H1 and H2, we need to measure the oil column as well as water column. Let me draw a horizontal line at common interface. Let's mark it here and mark it here. This is H1, H2. Oil column, I take it as H1 because that is what we change. So, ideally we should take it as H1 and accordingly the water level will balance, which is H2. If the density of coconut oil and water are given by D1, D2 respectively, write down a formula for D1 in terms of D2, H1 and H2. We have done this several times. We are experts in it now, isn't it? If I take the atmospheric pressure as pi, the pressure at this point will be pi plus H1 D1 G. D1 is the density of oil. Similarly, on the other side, pi here, H2 D2 G. Since it is in the same column, same water, right, same liquid at the horizontal level, same horizontal level, same connected liquid, same horizontal level, pressures have to be equal, right? They didn't ask you to derive it, they simply asked you to write down the formula. Otherwise, you are write it, if they say derive, you are write this point as A. Pressure at A has to be written first. Pressure at B has to be written next. Then you have to say PA and P will be equal because it's the same horizontal level within the liquid. Equating that, you have to derive it. Here straight away we can write it. Look at this. H1 D1 G, H2 D2 G. From this D1 will be equal to H2 over H1 into D2. Correct? Select the right method from the following methods in order to draw the graph for D1, for finding D1. Adding more water into the relevant limb or adding more coconut oil into the relevant arm. Do we add oil or do we add water? We did the experiment by adding oil. Every time we change the oil column's length. Why not water? Let's go and see. What happens if I see, if you add water into this, okay, something will happen, the levels will go up and all, but the quantity of oil is not going to change, right? If the quantity of oil doesn't change, H1 cannot change because the cross section is uniform. In this tube, the height of oil column cannot change. Unless you add more oil, the oil column's height will not change. Then come back to this equation. If H1 doesn't change, D1 and D2 are densities which are constants. So if H1 doesn't change, H2 also cannot change. So however the water of volume that you are adding there, your H1, H2 measurements will remain constant. You won't be able to get multiple readings to draw a graph. You will end up getting same H1 and same H2 every time after adding water. How is it possible? How is it possible? Let's check. When you put more water, what will happen? The common interface will go up. Look at this. Let's say it comes to this point. Common interface comes up. Common interface goes up means your oil column also will go up because oil's quantity doesn't change. So by the same amount it goes up, right? If I mark this as X, by same x it will go up. Not only that, on the other side water column also will go up. That will also go up by same x when you pour water. So what happens, can you see, now the extra water you have filled will be occupying this space, the additional space it has got on this side, and the additional space it has got on the other side, x, x. That's where the additional water you poured in will occupy the space. And look at the heights now. Common interface goes up by x, water level goes up by x, so height of water wouldn't change. Oil level also goes up by x, so the base goes up by x, top also goes by x, then the height of the oil column will also remain constant. So this is what happens when you add water into this, right? So remember, when we are using a more dense liquid and less dense liquid here, we usually add less dense liquid again and again to get multiple readings. If you get more dense liquid, then the heights will not change. The measurements you get, HL and HW, will not change. Let's explain that here. Did they ask you to explain it? No, they say simply select. So adding more coconut oil is what I have to do. Adding more coconut oil. Give the right reason for not selecting the other method. So let's say when more water is added, H1 and H2 will not change as the common interface and the meniscus of liquid columns will rise by same height. It all rise by the same height, therefore H1, H2 wouldn't change. Gradient of such a graph was 0.87. Find the density of coconut oil. Now see, what you have is this. H1 D1 equals H2 D2. So H2 will be equal to D1 over D2 into H1. Y M X. Why do I take H1 in the x-axis? H1 is the oil column's length. That's what we are changing. Independent variable is H1. And according to H1, H2 takes values. So H2 depends on H1. H2 is the dependent variable, dependent. And the gradient is D1 over D2. D1 is the oil's density, D2 is the density of water, So D1 over D2. Then we say gradient equals D1 over D2. 0.87. Oil's density, water's density. Cross multiply, you get 870 kilogram meter minus 3. Suppose if anybody has used the equation other way around, without thinking twice, if you have taken H1 equals D2 over D1 into H2, then the gradient would have been D2 over D1. And then when you get the answer, you will get 1000 divided by 0.87, which will be like 1150 or some value. The moment you get that value, you must understand you are wrong. Why? You are talking about coconut oil's density, which cannot be more than that of water. Water's density is 1000. So you need to get something below 1000. Right. So you have to keep your common sense open when you are doing questions. It's not just, memorizing from the books, going and repeating in the exam. No. Physics needs a lot of common sense. So every answer you write, you need to think, is it feasible? Is it possible? Will it work? That kind of questions must be working in the back of the mind. It has to be a continuous process in the back of the mind. In the front brain, you are working about answering, calculations, blah, blah, and all that. But there should be some part of brain always checking the answer in different means. Is it possible? Am I getting the right units for this answer? Did I compare this with that? That is what makes you from a B level of getting marks to get like 80 marks, 90 marks. That common sense, that matters a lot. So if you have got an answer above 1000, possibly because they never asked you to write the gradient earlier. So if somebody has taken other way around, H1, H2 other way around, you would have ended up having the gradient D2 over D1, which is wrong. But still, okay, you didn't realize it, you went all the way. When you get the answer, you must understand, yep, I made a mistake. Next, in this experiment, which liquid must be poured into the U-tube first? Give reason for your answer. Those who saw the experiment when we were doing, we were pouring water into that first. Why not coconut oil first? Right? You might have thought sometimes, it's okay, we can put coconut oil also, but no. I'll tell you why. This is your U-tube. Let's say you have filled it with coconut oil first. Now you are pouring water into it. Say you have some coconut oil in some bowl and you pour water into it. What will happen to the water? Water will go to the bottom because water is more dense than the oil. So oil is supposed to float in water. So even though oil is already there, when you pour water into that, water will go down. That's what is going to happen here. When you put water, water will penetrate all the way and it will come here. It won't go up again because again it's water, it's oil on the other side. So what will happen when you pour water? After you finish pouring water, you may have a situation like this. This is water and in both sides you have oil. This is possible. This is possible. Understand, this is what will happen if you have poured the oil first and then if you pour water into that. Clear? So they are asking which liquid must be poured first? Water. If oil is poured first, when water is poured next, oil columns may establish in both arms of the U-tube. To prevent this, water must be poured in first. Clear? Next. What should be the minimum height of a liquid column if the density of coconut oil has to be measured with a fractional error of 0.1? Assume that the length of a liquid column can be measured with 1 millimeter accuracy. Very nice of them, they have given you a hint also. They say fractional error in density is equal to twice fractional error of the height of the liquid column, delta H over H. And this is what they want it to be 0.1. Fractional error, they want it to be 0.1. 2 into delta H. Length measurement error can be 1 millimeter. 1 millimeter over H. So H is going to be 2 divided by 0.1, 20 millimeter. That is 2 centimeter. So at least H has to be 2 centimeter. 2 centimeter must be the minimum measurement you take such that density's fractional error is 1%. 1%. What is the disadvantage in using mercury instead of water in this experiment? What will happen when we use mercury? I have shown it to you, right? To balance mercury, even a small height of mercury will require a long height, a tall column of oil. So, I will show you some numbers. Look at this. When we use water and oil, dW is 1000 kilogram per meter cube. This is 870 as per what we calculated. So, suppose if HW is let's say 10 centimeter, this H oil will be around 12 centimeter. So, the heights are almost equal, right. So, if you put 5 centimeter length of oil column, water will go up by around 4 centimeter. So, you will have significant lengths to measure. Now, what happens when you use mercury? Mercury's density is 13,600. Oil's density is 870. So, when you put oil 10 centimeter, mercury will go up by, see 10 into 870 is 8,700. It will go up by approximately 0.6 centimeter, because you know HODO has to be HMDM. HODO has to be HMDM, right. So, when you put it in the equation, HM comes approximately 0.6 centimeter, right. Even if it goes up by 20 centimeter, it is going to be 1.2 centimeter. So, the change in the height of mercury column is small. Therefore, what happens? The fractional error in getting the mercury column's height will increase. Let us write it. When oil is poured in, the respective change in oil column will be very small. Oil column height, let us say oil column's height. Oil column height will be very small. This will increase the fractional error of measuring height. Understand? I have shown this also at the end of the experiment. I have shown what happens when you use mercury. Clear? Right. So, that is what, it is very simple and straightforward questions. As I always say, in mechanics and waves and oscillations, the questions that you get in structure are pretty straightforward. Only thing is, you need to have the understanding about basics. Like what many students do sometimes, they just memorize the experimental steps that are given in the books and go to the exam. Now, that is good, but without the fundamental understanding, without the understanding of basics, if you have memorized it, some of the questions you will not be able to answer, because they do not ask always the same question. They sometimes, like couple of parts, they add new things into the question as well. So, you must be able to think, maybe like first few questions you can answer, right? Draw the diagram, write down the steps, what measurements do you take, how do you calculate, this is the routine, you can answer all of them. But you know, when they make some changes, when they introduce some twists into that, you will not be able to answer. So, make sure, go through the experiment that we have done, understand the experimental procedures with the reasons why we have done this. That is very important. With the reasons why we have done, understand the experimental procedures and try these questions. Next session, let us meet up with another experiment.